All right, so this is page 2 of the Unit 4 Part 1 packet. This unit's all about ionic bonding, but we're doing a little tiny brief intro to metallic bonding, and then the rest of the unit's about ionic bonding. So for metallic bonding, we already said on page 1, it occurs between metal atoms only. That's why it's called metallic bonding. And in metal compounds, we have lots of loosely held electrons that are in those atoms, and then when we have a whole bunch of those atoms, we have all those electrons that are loosely held. Those electrons can move freely throughout the entire sample. So they're basically free-range electrons. They belong collectively to the sample. They don't really belong specifically to any one atom. These electrons do not belong to any one atom in particular, so metallic bonds are usually described as a sea of electrons, where they kind of can ebb and flow. The electron's ability to move freely is responsible for characteristic properties of metals that we saw in one of our earlier units. So for example, the idea that they are ductile and malleable. So ductile means that metals can be stretched into wires without just snapping. Malleable means that they can be flattened into sheets and rolled, so that's how they make aluminum cans. So if those sea of electrons, if they weren't willing to move freely, then if you took a hammer and hit a piece of metal, it might shatter instead of spreading. They are also good conductors of heat and electricity. Electricity is just electrons that are moving from one place to another throughout a sample. So when we say that they're good conductors, this is really because their electrons are free to move. So again, this idea that all these electrons, if I wanted electricity to flow, we could put some electricity, plug it in, and all these electrons could flow and go out through the other side. If we were to take a hammer and hit a metal sample, those electrons are free to slide, and so again, that whole sample can slide instead of shattering. That is as much as we get into with metallic bonding. So the rest of the unit is all about ionic bonding. All right, so as a reminder from before, we have something called the octet rule. Remember, oct, the prefix means 8. So noble gases, which are the elements in the far right column on the periodic table, these are elements that are stable, that don't want to form bonds, and they are stable because their outer shell of electrons contains 8 electrons. That's kind of a magic number for valence electrons. Other atoms also want to achieve this stable arrangement, so what other atoms are going to do is they're going to try to get to 8. They might gain. So if an element has 7 valence electrons, it might gain 1 to get to 8. It might lose. So if an element has a full shell and then we went 1 farther than that, then it might have 1 valence electron. It can lose that 1 valence electron and its previous shell was full. Or sometimes they're going to share. So some elements will say, I have 7 and you have 7. What if we kind of pretend like we're sharing one of mine and one of yours so that we both feel like we have 8? Again, the goal here is to try to get to this magic number of 8 valence electrons. So ionic compounds, these are the ones that are formed by gaining or losing, not sharing. Sharing is covalent. So in an ionic compound, a substance is composed of atoms whose electronegativity values. Remember, electronegativity means how much an atom pulls on electrons in a bond. So we have 2 different atoms whose electronegativity values are so different that one atom takes electrons away from the other. This is essentially going back to the idea of the tug-of-war. If we have one tug-of-war competitor who's really strong and one tug-of-war competitor who's really weak, then the person who's strong can just take from the person who's weak, and there's just a transfer, right? One person wins, one person loses. And when this happens, then one atom gains, one loses, we have ions. So we have a cation, that's one element becomes positively charged, and then we have an anion, the other one becomes negatively charged. So that electron is transferred, we create ions. This large difference in electronegativity happens when we have a metal. Remember, metals are on the left side of the periodic table. They have low electronegativity values. It's going to bond with a nonmetal. A nonmetal is found on the right side of the periodic table. Nonmetals have high electronegativity values. So if we have a metal and a nonmetal, we have that transfer of electrons. There's also a little note. We also have something called polyatomic ions. We'll get to that later in the unit, but it's just kind of a little side note here. We can also have those so that when we learn that and you come back and look at this definition, it's not missing. All right. Ionic compounds consist of large numbers of ions held together in what's called a crystal lattice structure. We don't have individual molecules, we just have the repeating pattern over and over and over that forms a geometric shape. So in this case, this is sodium chloride, which is table salt, and the formula for that is NaCl. So we have NaCl, 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 and it just repeats over and over and over, and in this case, it forms the shape of a cube. So when we write the formula for this, I don't know if there's 1 million or 2 million or 5 million different atoms that are actually in this grain of salt, but what I do know is the ratio. In this case, for every 1 sodium, there's 1 chlorine. So the way that we write the formula, we call it a formula unit. So instead, when we write the formula for it, we write a formula unit, which indicates the simplest ratio of the ions. So in this picture, we have NaCl, even though that pattern has repeated in this picture maybe 20 times. We'd still just write NaCl. All right. Valence electrons. This is a review from before. These are the outermost electrons in the atom. So when we draw our Bohr model, they're the ones in the outermost ring. They're involved in forming bonds. All of the core electrons that are located closer to the nucleus for atoms, those aren't involved in forming bonds. Elements in the same group, which means column on the periodic table, have the same number of valence electrons, and we can use the octet rule to predict what charge ion each of these different families will form. So remember that this is the goal. This is where all elements want their electron number to be. So if we look at this, we can say, okay, 8 is the goal to get to. Well, how far over do elements have to move in which direction? Do they move to the right or to the left to get there? So if we start over here, this column is only 1 away. So this has a charge of 1. This column is 1, 2 away. This column is 1, 2, 3 away. And when we look at that, in all of these cases, the fastest way to get to this column is to move to the right. I want to move to the right 3 or the right 2 or the right 1 to get there. This is gaining electrons. You usually think of gain as meaning positive, but remember that electrons are negatively charged. So if you gain electrons, you actually become negatively charged. So these 3 columns have those charges. Everything in this column makes a -3, -2, -1. If we look at some of the other columns on the periodic table, we skip the transition metals altogether. So we're going to totally ignore this section of the periodic table. They do different things. So if we look at some of the other columns, and we look, for example, at this column over here, the fastest way to get over to the noble gases is not to move towards the right, it's actually to move backwards. If this element moved backwards 1 square, we'd be over here. And so everything in this column is actually also still 1 away from becoming like a noble gas. It just needs to move backwards 1 instead of forwards. Everything here would move backwards as well. Backwards 1, 2 to get over here. And then these elements would move backwards as well. Backwards 1, 2, 3 to get to the noble gases. These ones are all moving backwards, which means they're losing electrons. Usually losing means negative, but again, because electrons are negative, when I lose a negative, I become positive. This column right here would be, we would assume a 4, but is it a +4? Is it a -4? It kind of gets confused and we don't really know. So that column does something different. And so we're going to come back to that column later on. It basically just, most of those elements don't want to make ionic bonds. And the ones that do make ionic bonds, we still need a little bit more information to figure out what their charge is going to be. So that's a review of valence electrons, and we're going to use these charges in order to figure out how to write ionic formulas for these different compounds coming up.